on to the deliberate mistakes. Sometimes it's important to put in a deliberate mistake on the board so that it gets you thinking, and so you can come and correct it afterwards. So you understand that this was a deliberate mistake here. I got this the wrong way up. It should have been a half. And thank you for noticing it, and thank you for correcting me. Another interesting issue that arose over the break is I showed you here, somewhere, I showed you the relationship between the forward and the reverse rate coefficient and the equilibrium constant. And that relationship obviously applies at equilibrium. But does it apply under non-equilibrium conditions? And yes, it does. So that there is something called, and it's on the slide, but I failed to mention it, there is something called the principle of detailed balance. And this says that this equation here certainly applies to equilibrium, but it applies under any conditions. So those rate coefficients don't change as you move away from equilibrium. So if you've got a combustion system, those forward and reverse rate coefficients are still linked via the equilibrium constant. What doesn't happen now is that the rate of... One thing that is important to remember is the difference between rate and rate coefficient. Here we're talking about rate coefficients. The rate is equal to dx by dt. And the forward rate is equal to the reverse rate at equilibrium. It isn't equal to the reverse rate away from equilibrium. So the forward rate will only equal the reverse rate at equilibrium. But the forward and the reverse rate coefficients are always related to that equilibrium constant. Okay? Is that clear? This is a really important issue. And somebody who uses Chemkin raised it and said, didn't really understand whether it still applied away from equilibrium. But that relationship between the rate coefficients always applies because of this principle of detailed balance. Okay, so that's an important point. There was something else as well, but as you get older, you forget things. And somebody else raised an issue. Just goes to show how gullible I am. Okay, so the next deliberate mistake was to accept do we all agree? One of the problems is you should always write all of your notes out before you commit them to the blackboard. And I was hacking that. It was going on in my head. And having things going on in your head in front of a lot of people is difficult.
I don't understand. So I thought it made sense because for every HO2 you lost, shouldn't you get 1/2 H2O2?
Yep.
But isn't that saying for every HO2 you lose, you get 2 H2O2s?
No, but what we're talking about here, the rate of loss of HO2 is going to be twice the rate of loss, the rate of formation of H2O2. Because for each HO2, you form only half an H2O2, the rate of HO2 is going to be twice the rate of formation of H2O2. Think about it, and we can always revisit this, but have a think. And okay, anything else from your cogitations over coffee? Okay, this is great. Thanks very much for all of these interactions. This is exactly, it's quite hard to be really interactive with a large group like this, but that's what we've got to really try and do. And if we do less of it because of all this talk, that's okay, because you've always got the notes.
Professor?
Yep.
I have a question on that principle of detailed balance.
Yeah.
Is that, where exactly does it come from? Does that relation come from? Do you extend from the equilibrium condition, or I'm talking about non-equilibrium condition?
Yeah, it's simply the property of, it's simply the property of and the definition of rate coefficients. So the rate coefficients are defined in terms of a forward flux. So you look at the forward reaction in isolation. And so it just depends upon the concentrations of the reactants. And we'll show tomorrow how you do that. You calculate that forward flux. And then by going to equilibrium, you can demonstrate that those rate coefficients, the ratio of those rate coefficients, must be related to the equilibrium constant. And because they're constant, because of the way that you've calculated them, then this ratio applies under all conditions. You can also do it through a variety of thermodynamic approaches as well. But in many ways, for us, a heuristic approach based on the way in which we can calculate those rate coefficients is the easiest one to understand. Does that help? Right. Okay. After an hour, I can now give you the synopsis of what we're going to talk about. So today we're going to talk about experimental measurements of rate coefficients and product yields for elementary reactions. Tomorrow we'll look at linking experiment and theory. I've called these topics 1 to 7 because, well, obviously they're not going to last a whole 3 hours, each of them. Some of them will actually run over 3 hours. Some of them will be an hour or even less. We're then going to look at the links between experiment and theory. And that's going to be fairly tough. Tough for me as well as for you. But the key thing, what we'll try and do is to make sure that we all understand. And if you're not understanding, we'll take it more slowly and take questions. We'll talk about thermodynamics. As you've seen, thermodynamics is really essential as far as combustion is concerned. We'll discuss the evaluation of rate coefficients. As you'll see, measurements of rate coefficients from one laboratory can disagree with measurements from another laboratory. Who's to say which measurements are correct? And there are what are called evaluation panels, wise men. They are exclusively men, it turns out. But there's no reason why women should be excluded from this process. So wise people look at those measurements and make recommendations. They evaluate those rate coefficients. We'll then look at mechanism construction and evaluation. On the last slide, we talked about the importance of mechanism evaluation here. So we'll talk a little bit about mechanism evaluation. And then we'll look at NOx chemistry. What we'll do is take 3 reactions that are central to NOx chemistry and look at the way in which they've been investigated and the rate coefficients determined. And then finally, I said that one of my interests is atmospheric chemistry. And what we'll do is we'll look at the relationship between combustion emissions. Combustion emissions are really important in determining what happens in the atmosphere, both on a local, a regional, and a global scale. So we'll look at the relationship between combustion emissions, air quality, and climate change. That's there really to set a lot of the work that we do in context. Some of you may have come across some of the issues that, well, I'm sure all of you will have come across some of the issues that are involved. But some of you will know some of this stuff in detail. I suspect that the vast majority of you won't. And so this is, in a sense, a sort of educative. I suppose the whole thing is educative. But this is really giving you background information that I personally think combustion engineers should understand. OK, let's have a look at measurements of elementary reaction rate coefficients. So we're going to concentrate on reactions of atoms and radicals, say something briefly about the reactions that don't involve radicals and are not involved in the initiation step. So we're going to concentrate really on radicals. We need to cover the range of temperature from 1,000 to 3,000 K for reactions involved in high temperature combustion, and from, say, 600 to 1,000 K for low temperature autoignition chemistry. We also need to understand kinetics in the range 200 to 300 K if we're interested in atmospheric chemistry. And there's a lot of overlap between the low temperature combustion chemistry, the types of chemistry that are involved, and the chemistry involved in the atmosphere. So ideally, if we're measuring the rate of an elementary reaction, we should isolate the individual reaction and study it under appropriate combustion conditions. This isn't always possible. We may have to model a system to extract the rate coefficients of interest under the conditions we need them, and so extrapolate to appropriate conditions of temperature and pressure. And ideally, we achieve this with the use of theory combined with experiment. So we do the experiments, and then we extrapolate using theory. OK, the techniques we're going to talk about are pulse laser photolysis, which is the technique that our group in Leeds is involved with, shock tubes, and Professor Hansen will be talking inter alia about shock tubes. If you're not going to his lectures, then you can always look at his lectures on the web after the summer school is over. And I would really encourage you to do so because he knows an awful lot more about shock tubes than I do. Flow tubes for elementary reactions. You've seen Fred Dreyer's flow tube, but there are other sorts of flow tubes where you can measure rate coefficients directly for individual reactions. And then what I've called static studies of whole systems. So let's have a look at pulse laser photolysis. This is a typical experiment. We have a laser here, which is an excimer laser, in this case operating at 248 nanometers. And here's a reaction cell. And we flow, we're looking here at reactions between OH and a reactant. So we flow the reactants with a precursor, something that when photolysed will produce OH, and a third body or a diluent through the reaction cell, and we hit it with this laser here. The laser pulse lasts about 20 nanoseconds, and what it does is it photolyzes this precursor and generates OH on that short time scale of the order of nanoseconds. We then have a second laser. In this case, it's a neodymium YAG laser that's pumping a dye laser. And this dye laser is tuned to 283 nanometers. And the point about 283 nanometers is that the OH radical absorbs light at that wavelength. So the OH gets absorbed, the OH absorbs a photon of light and gets raised to an excited electronic state. And again, this is a topic that Professor Hansen will discusses in detail in his lectures. And if you're not going to his lectures, then have a look at those, at his notes, and have a look at the video of his talks. And you can understand this then in much greater detail. So OH absorbs that photon and then fluoresces. So it emits a photon. The OH emits a photon of light, and we detect that photon on a photomultiplier. Or we detect a whole set of photons from different OHs on that photomultiplier. Okay, so pulse of light generates OH at time 0. It then reacts with the reactant, and we probe it at a particular time using this dye laser, and we probe it through by looking at the fluorescence, so what's called laser-induced fluorescence. So this is a laser flash photolysis, or sometimes called pulse laser photolysis, laser-induced fluorescence technique. And we set the time delay between the photolysis laser, this laser here, and the probe laser, this laser here, and we measure the intensity of the fluorescence at that particular time delay. And then we repeat it with different time delays, many, many, many times. These lasers fire typically 1 a second, and you might do an experiment over 10 minutes or 20 minutes or even an hour. So the beauty of this technique is that you use time averaging, and the time averaging allows you to measure concentrations which are very, very low. And I'll explain why that's important in a minute. So we repeat this at different delay times, and repeat, and so we generate a decay that looks something like this. So this is a decay of the OH fluorescence as a function of time, and you can see that it's decaying on a time scale. These are in microseconds, time scale of the order of 1 microsecond. Sorry, 1 millisecond, 1,000 microseconds. The signal is proportional to e to the minus kt. So OH is decaying away, and it's decaying away exponentially. Now, why is that? Let's explain what's going on there. So let's say we're looking at OH plus H2. And we set up the conditions such that H2 is going to be very, very much larger than OH. So if we look at OH, that's going to be equal to OH 0 times the exponential of minus k times H2 times OH. But because of this condition here, the H2 concentration is going to be constant. The amount of H2 that's going to be removed is minute. There's going to be a little bit removed because it reacts with OH, but that amount is going to be minute. And so we can rewrite this as OH0 times the exponential of minus k prime times t, where k prime is equal to k times H2. And so the decay is exponential. And that's really important. And these conditions are called pseudo first order. So they're pseudo first order conditions. It's a second order reaction, but we're looking at it under pseudo first order conditions.
What happened to the concentration of OH in the exponential, and where did your T come from?
Oh, hang about. Thanks very much. Should have written that. So OH is reacting away with a rate coefficient K times H2 times T, and it's exponential because H2 isn't changing, it's constant. Thanks very much. So OH is equal to OH0 times e to the minus K prime T, where K prime is equal to K times H2. Okay. We can rearrange that. Then we get that OH over OH0 is equal to exponential of minus K prime T. So the shape of the curve is independent of concentration. If we doubled the OH concentration at the start of the experiment, we'd still get the same shape of the curve. And that's important because we're using laser-induced fluorescence, and the intensity of fluorescence is proportional to the concentration of OH. But we don't need to know the constant of proportionality. We don't need to know that. We only need to know that the intensity is going to be proportional to OH because of this relationship here. So that's a really important attribute of keeping these pseudo first order conditions. So let's go through what happens. So this slide is taken from an undergraduate textbook. So it's a simplification, but I think it's a very nice simplification. That could be because the textbook was written by my wife, but be that as it may. So here's a flash photolysis experiment. So we have a laser which a short pulse of light into the reaction cell. It generates OH, and in this case, those OHs are reacting with SO2. And we monitor the OH as a function of time using laser-induced fluorescence. So we get OH versus time, but the signal is only proportional to OH, but that's OK if the reaction is pseudo-first order. We can then plot the logarithm of OH versus time. Basically taking this relationship here, taking logs, we'll get a straight line, and the gradient of that line is equal to K prime, which in this case is equal to minus K times SO2 because we're looking at OH plus SO2. We then repeat this experiment at several values of the SO2 concentration. So we keep that SO2 concentration very much larger than OH still, but we do the experiment many, many times, and then we plot K prime versus SO2. And since K prime is equal to K times SO2 0, then plotting K prime versus SO2 0, the gradient is going to be equal to the rate coefficient for the second order reaction, which is what we want. So that's the sequence of reactions. So it takes a while to get these rate coefficients. You've got to do the experiment. Each of these experiments you do many times to generate this decay curve here. You then get K prime, and then those K primes you can turn into second order rate coefficients by using this, by plotting versus SO2. I've said SO2 0, but that SO2 0 is invariant during the experiment, during each experiment. but we change the SO2 zeros going from one decay to another. Okay, is that reasonably clear? Here's another example, OH plus acetylene. And this reaction forms this species C2H2OH at low temperatures. So it needs a third body, M, to stabilize it. The rate coefficient is dependent on pressure. And so now we've got to look at the rate coefficient as a function of both temperature and pressure. And so here's an example of a decay curve and a single set of conditions. Here's a plot of the observed rate coefficients, pseudo first order rate coefficient, what I call K prime, versus the acetylene concentration. You see a nice straight line. And from that, we can get the rate coefficient, the second order rate coefficient, at a particular pressure and at a particular temperature. And then we repeat the experiment at a range of temperatures and a range of pressures. We can then analyze that, and I'll talk a little bit more about that tomorrow. Here's an example of an experiment, OH plus acetone. And the point that I'm trying to make here, and there's a slight change in wording here, which you might want to correct. There's the rate coefficient as a function of temperature. And notice that it's really fairly complicated. The rate coefficient decreases as the temperature goes down, but then it starts to turn around and slightly increase at lower temperatures. And there are interesting theoretical reasons for that. But the key thing here is that the pseudo first order rate coefficient that you get out, so K prime now is going to be equal to the rate coefficient times the concentration of acetone. And any systematic errors in the acetone, in your measured acetone concentration, is going to be reflected in the rate coefficient. So you've got to measure that acetone concentration as accurately and as free from systematic errors as you can. And so in this particular experiment, I won't go through it in detail, they use absorption spectroscopy both before and after the reaction cell to measure the acetone concentration so they can pin it down as accurately as they possibly can to 1 or 2%. I've talked about laser-induced fluorescence, and let me make one point about laser-induced fluorescence and about pulse photolysis generally. And that is that you can work with the concentration of hydroxyl you can work with is of the order of 10 to the 10 molecules per centimeter cubed. You can work out what that means in terms of molar concentrations by dividing by 6 times 10 to the 23. But that's very low. And you can do that because of the time averaging. And the intrinsic sensitivity of the laser-induced fluorescence process. Now, why is that important? It's important because secondary reactions are unimportant. So when you do an experiment, when you generate a radical using pulse photolysis, and when that radical reacts, you generate other radicals. But the concentrations of those radicals are going to be of that same sort of order. They're going to be of the order of 10 to the 10 molecules per centimeter cubed. Now, the fastest That's bad English. The highest rate coefficient you can get is of the order of 10 to the minus 10 centimeters cubed per molecule per second. So that means that these secondary reactions, the time scale is going to be of the order of the rate coefficient times the concentration of the other radical, which is going to be 10 to the minus 10 times 10 to the 10. Sorry, 1 over that. So the timescales for these reactions are going to be of the order of 1 over 10 to the 10 times 10 to the minus 10 seconds. In other words, they're going to be of the order of a second. We're looking at the experiments on a timescale of about a millisecond, and so these secondary reactions are making a minimal contribution to the decay of the radical on the experimental timescale. So let me just recap without the numbers. What that means is that because we can use this signal averaging process, because of the sensitivity of laser-induced fluorescence, using pulse photolysis coupled with LIF, you can look at reactions in genuine isolation so that secondary reactions are unimportant. So let's have a look at some other techniques. So this is a technique using mass spectrometry. So this is replacing the laser-induced fluorescence technique by a mass spectrometric technique. I won't go into detail, but it's basically using photoionization, using a VUV laser to photoionize the molecules in the reaction cell, extract them into a time of flight spectrometer, and measure their relative concentration using mass spectrometry. There are some really superb examples of the use of mass spectrometry at synchrotron facilities in the United States and in China. So these use synchrotron VUV photoionization. The point about a synchrotron is that you can tune the wavelength, and that's an essential attribute of this technique. So you can tune the wavelength, and you can change the photon energy that leads to production of the ions. And so this was not a kinetics experiment. This was an experiment that looked at the species present in a flame and looking at the mass over the charge of 44. So the photoionization simply leads to ions which are singly charged. So this is basically mass of 44 for different flames. And they were looking for acetaldehyde, CH3CHO, which they knew to be produced in these flames. And so this is a signal related to acetaldehyde up here, but they found that there was a signal that occurred at lower photon energies, lower photoionization energies, something that had a lower photoionization threshold. And this species at this mass must be ethanol, this species here, which is an isomer of acetaldehyde. Ethanol, and so you can see that at these lower photoionization energies, where acetaldehyde is not photoionized, you're producing ions at this mass, and these must be due to ethanol. And what they can do is they can calculate what the photoionization energy threshold would look like for ethanol at these experiments. So this demonstrated very clearly that another word for this is vinyl alcohol, is produced in these flames, and it was not previously thought. These are experiments in China, looking at the same species. These are little. So this is a couple of years later in China. Very, very nice signal-to-noise ratio. There's the acetaldehyde production. The production of ions corresponding to acetaldehyde. Here is the production of ions corresponding to ethanol. The ionization energy of ethanol is 9.33 electron volts. That of acetaldehyde is 10.23 electron volts. So this is a really very beautiful example of the way in which these synchrotron facilities can be used. They can also be used to look at kinetics, and so these are experiments by Craig Tages and David Osborne in the Sandia National Labs. And so this is the reactor here. So they have an excimer laser pulse that comes down here, generates species which then react, and then they analyze them using the mass spectrometer, using, again, the synchrotron radiation to do the photoionization process. And this was an experiment. This is a fairly mind-blowing experiment that's important in atmospheric chemistry, particularly. What they did was to take CH2I2, photonize it. The way in which we write photolysis is to put H nu, yet another nu. I'm sorry, this is the frequency of the radiation. This is Planck's constant. So that simply means a photon. So this is a reaction involving the photon, which produces CH2I plus I. CH2I reacts with O2 and forms I plus CH2OO. And this is what's called a Kriege intermediate. It's a biradical because it's got two unpaired electrons, one on the carbon, one on the oxygen. And it's important in a range of atmospheric processes involving ozone and organic compounds. And it had never ever been seen before. It had never been detected. It had been invoked in mechanisms, but it had never been detected. And so what could be happening is that this reaction here could be producing this species here, which is more stable, but isn't a Kriege intermediate. But what they did was, again, to use the synchrotron facility. And so this is the photon energy going up here, and here is the signal that they see. And they calculated the photoionization curve for this Kriege species, CH2OO, which looks like that. And then they calculated that for this species, dioxirane, and that looks something like that. And you can see there's a bit of an increase here, which corresponds to the dioxirane. And they did separate experiments on the dioxirane. But this shows very, very clearly that provided they're working in photon energies down here, with this experiment, they're detecting this Kriege intermediate. Never been seen before. And so they can then look at the kinetics, and there are all sorts of interesting results coming out now from these experiments. This was done in 2008. Many experiments done since then showing improving our understanding of the way in which these Kriege biradicals work. So that's synchrotron, the use of synchrotrons in photoionization. Here's another sort of technique using, this is going back eons, and this is using absorption spectroscopy to look at a species of a radical. And so this is looking at the R radical. So the R radical is C3H5, and we're looking at R plus R. So the reaction in this case is second order in radical. And so we now need the absolute concentration of the radical to determine decay. If we, so we're going to get that minus dC3H5 by dt is going to be equal to 2 times the rate coefficient times C3H5 squared. And if you integrate that, what you'll find is that 1 over C3H5 is equal to 1 over C3H5 0 minus 2 times K times T. If you set that equal to C3H5 0 over 2, and this here to T a half, then you can calculate the half-life of this reaction. And the half-life turns out, if you go through this substitution, is equal to 1 over 2 times K times C3H5. So now it depends on the concentration of the species. So we need to know the concentration of that species absolutely in order, the absolute concentration in order to work out the rate condition. So this is a decay profile. And if you look at that, then you can see that it's certainly not exponential. The decay is slowing down as you go to longer times because the concentration of C3H5 is decreasing. And so what you do is you use the Beer-Lambert law, which again you can get more detail on from Professor Hansen's lectures. So this is the light coming through the reaction cell divided by the light going in. If you go back to this slide here, we look at the light going through the reaction cell compared with the light, I better explain the way in which the experiment works. What we've got is a reaction cell here, a xenon arc lamp, so light goes through the cell into a monochromator, and we have that monochromator set to a wavelength where the allo radical absorbs. And we use a laser beam, again, to generate the C3H5 here in a pulsed manner. Again, where you can use signal algorithm. And so I naught is the light intensity going into the cell, I is the light intensity coming out of it at this particular wavelength which the monochromator is set. And so there's a decay of the percentage of light that's absorbed. So the light that's absorbed is I minus I naught. I naught minus I. And so that's decaying away. And what we're doing to analyze it is using the Beer-Lambert law, which says that the transmitted light intensity divided by the incident light intensity is equal to the exponential of minus the absorption cross-section multiplied by the C3H5 multiplied by the path length. And in order to interpret this and from it get the concentration of C3H5 you need this absorption coefficient here, sigma, and obviously also the path length. So that's the way in which you get the absolute concentrations for these sorts of experiments where we're looking at second order reaction. Another absorption technique is cavity ring down spectroscopy, in which what we do is we take a laser and put the light from the laser inside this so-called cavity with high reflectivity mirrors at either side. What happens is some of the light leaks out the other side, and we monitor the intensity of this light. We use a pulse laser, and the intensity of that light decreases as a function of time. What happens is the light bounces backwards and forwards, a little bit leaks out, and because of that little bit leaking out, then the light intensity will decay as a function of time. The better the mirrors, the higher the reflectivity, the longer this decay is going to be. We then put something inside the cavity that absorbs, according to the Beer-Lambert law here, and we again measure the decay time, and from the difference between these, we can get the concentration of the species that's in the reaction state. And this is a very, very sensitive method, and is increasingly used in kinetics. So there's the way in which you set it up, the tunable pulse laser going into this cavity, and then you're measuring the intensity using these photodetectors. And we've applied this to HCO radicals, and this is a spectrum of HCO, so we set our laser at a particular frequency at which HCO absorbs. One of the things that I mentioned was that it's important that we not only we not only know the rate coefficient for the reaction, but we also know the products if there's more than one set of products. This is looking at reactions of CH2. We'll talk about CH2 tomorrow, or probably on Wednesday. CH2 is methylene, and this is what's called singlet methylene, where the electrons are paired. It has two electrons which could be either unpaired or paired. And so this is singlet methylene, which reacts with H2 to form CH3 plus H. And this reaction can also do other things, and we need to know the yield of H in the experiment. And so what we do is we have one laser that looks at CH2, and looks at so we produce CH2 in the laser pulse. These are now quite short time scales of about 10 microseconds. Produce CH2 in the laser pulse, it decays away, and then we have another laser, a vacuum ultraviolet laser, that looks at H. And so we can look at the production of H as a function of time. And you can analyze the rate coefficient for the decay of CH2, the rate coefficient for the production of H, and they're the same within experimental energy. But in addition, what you can do, if we calibrate these laser-induced fluorescence signals, and there are ways of doing that I'll explain on Wednesday. If we calibrate the signals, we can work out what the yield of H is, whether each CH2 that decays away produces an H, or if it produces only a fraction of an H. You see what I mean? And this is an important experiment that again was done at Sandia National Lab, looking at C2H5 plus O2. And so what they're doing is they're looking at C2H5 decaying away. Sorry, they're not doing that here. They're looking at C2H5 plus O2, so they can look at the decay of C2H5, but they can also look at the way in which HO2 behaves. And so here is what they're doing here. This illustrates the way in which this calibration process is done. So here's the overall reaction mechanism. C2H5 plus O2 becomes C2H5O2. That then reacts, that can then be stabilized to form a peroxy radical here, or it can react to form HO2. Or this C2H5O2 stabilized can be energized to form C2H4 plus HO2. So there are two possible ways of producing HO2 in principle. What they did was to look at HO2. And they calibrated the signal by looking at chlorine atoms. They generated the ethyl radicals from chlorine photolysis. Chlorine reacts with C2H6 to form C2H5. So Cl plus C2H6 forms C2H5, and then that reacts with O2, and amongst other things, it produces HO2. In addition, what we can do is we can take Cl plus CH3OH, that forms CH3O plus HCl, and this down the HCl here. And the CH3O reacts with O2 and forms HO2 plus HCO. And that HO2 is formed in 100% yield. So this particular reaction gives HO2 in 100%. So you can see here, so there's the HO2 from Cl plus methanol. Here's the HO2 from Cl plus C2H5 at low temperatures, 423 K. And you can see that the C2H5, the HO2 is produced instantaneously, and then it decays away in both experiments. We produce very much less HO2 in the ethane experiment than we do in the methanol experiment. And then this is higher temperatures, and again we produce HO2 instantaneously, again with relatively low yield, but then the HO2 begins to build up as a function of time and then decay. And so what this experiment demonstrates is HO2 is being produced by this mechanism on short time scales and by this mechanism on longer time scales. Here's the direct production of HO2 here from C2H5O2 star, and here's the slower production in this reaction now. And this is a really central and important observation as far as auto-ignition chemistry is concerned. And we'll discuss this in greater detail tomorrow and then later on. Okay, let me say something very briefly about shock tubes. As I said, you can get far more information by looking at Professor Hansen's discussion of shock tubes in his lecture notes. But let me say something briefly about them. So the point about a shock tube is you have a high pressure driver region here and a low pressure region here contained in this shock tube. So the low pressure region contains the reactive system. And what happens is you have a diaphragm here that is perforated, and this high pressure shock drives its way through the this lower pressure region and heats it compressively. So you get compressive heating of this low pressure, formerly low pressure region here. And then the shock front can hit the back wall, and then you get a reflective shock which increases the temperature even further. So you can look at the reactions under the conditions in the incident shock wave and also at higher temperatures in the reflected shock wave. And one of the key things that Professor Hansen discusses is the period of time that is available to you to do these experiments and the way in which you control that period of time. So here's a picture of his lab. If any of you haven't been there, it's an education to go and see this laboratory. It's absolutely superb. Several shock tubes all set up for doing kinetics and related experiments. Okay, so shock tubes rely on compressive heating of the reaction mixture. The radicals are generally formed from the thermal dissociation of the precursor. It's single shot, so it's not possible to do single averaging as you do with photolysis. You generally need to, as a result of that, the concentrations of the radicals are necessarily high because you've got to be able to detect. We use signal averaging to detect them in photolysis systems. You can't do that in a shock tube system, so you necessarily, therefore, have higher concentrations. And that gives rise to secondary reactions. And you've got to make sure that you take account of those secondary reactions. That's the downside of shock tubes. The upside of them is that you're operating in this high temperature region, which is directly important as far as high temperature combustion is concerned, which is a region which is inaccessible using photolysis. So you can use these results directly without needing recourse to theory to extrapolate them to the conditions of the combustion system. So there are pluses and there are minuses. It's a very big plus, though, that you can operate under these types of conditions. And here's an example. This is measurement of the CH3 plus OH reaction by the Hansen group. There's the reference. Throughout this, I've tried to give you the reference to all of the examples that I'm providing so that you can go away and have a look at those examples to get more details. And this is what's called the sensitivity coefficient for OH. You're monitoring. One of the things that I omitted to say was that one of the crucial developments in shock tubes over the past several years has been the use of laser diagnostic techniques, and that lies behind much of Professor Hansen's lectures, and his group has been central to the development of these diagnostic techniques for shock tubes. So what they can do is they can look at multiple species using highly sensitive techniques. So although they can't get away from the secondary reactions, they can reduce them in importance. So this is looking at OH, and here's the OH mole fraction as a function of time. And there's the decay of the OH, and they're getting the rate coefficient by analysing this decay and comparing it with a small chemical mechanism that they've constructed based on the number of species that are decaying. And this is the best fit profile. Here's the profile if they reduce the rate coefficient by a factor of 2, and if they increase it by a factor of 2, and you can see that the decay is really very sensitive to this particular reaction we're interested in, CH3 plus OH. And here's a sensitivity analysis. The OH sensitivity as a function of time. There's the sensitivity with respect to the CH3 plus OH reaction. This is the sensitivity with respect to the reaction CH3 plus CH3, which is positive, so that removes CH3 and so increases the constant. Well, the concentration of OH consequently decreases less quickly. And then other reactions, C2H6 plus OH, acetone plus OH, which is related to the way in which OH is produced, and triplet CH2 plus OH. All of these rate coefficients here are well known. This one is less well known, but the sensitivity is relatively smooth. And so by analysing these, they can get a good rate coefficient for the forward reaction. Very interesting. Okay, right. Well, we better break until 11:15, and we'll come back, and then we can have another few minutes. Excuse me. And then any questions that you have, and then we'll carry on. Thanks a lot.